Welcome to the Inaugural Center for Connected and Automated Transportation Research Review. I'm Debbie Zena, the Managing Director. CCAT is the U.S. DOT Region 5 University Transportation Center. This is the first series of webinars that will showcase the impactful research that is being conducted at CCAT. Before I begin, I have a few public announcements. First is Michigan Annual Conference, September 25th and 26th. CCAT is an event sponsor, and there will be many prominent panelists and demos at the American Center for Mobility. I highly recommend attending, and you can register on the ITS Michigan website. Also, we have a list of upcoming events. I'm just waiting for the slide. There we go. On October 16th, we have a distinguished speaker series with Dr. Larry Head on 24-2020, so next spring, distinguished speaker series with Azim Eskin. And then in April 14th and 15th is our annual CCAT Global Symposium on Connected and Automated Infrastructure and Vehicles. Will be held in Ann Arbor. Highly recommend that as well. One last thing is please mute your mic for the duration of the presentation. And now I'd like to introduce Dr. Sridhar Lakshmanan from the University of Michigan, who will be discussing reliable communication network applications in platooning.
Thank you, Deb. Good afternoon, everybody. I'm Sridhar Lakshmanan. This is joint work with two of my co-PIs, Paul Richardson and Paul Wada. So we are in the 2019 cohort of CCAT funded projects, and as Debbie mentioned, it's on reliable V2V communication networks, especially in terms of its application in fuel-efficient platooning. And in addition to CCAT, we also received some funding from MCity on this project. Yes?
Would you like to share your screen, please?
I did. Let me do it again. Better now?
Yes, thank you.
Before I begin talking about fuel efficient platooning, I'm going to take a minute to go through the agenda, if I may. I'm going to spend a few minutes on Dearborn. Most of you are familiar with U of M Ann Arbor. It's been my experience that many are not familiar with U of M Dearborn, so I'm going to take a couple of minutes. I'm going to talk about fuel efficient platooning in general, why do it, sort of thing, without any particular reference to radio networks. Then I'm going to have a short break, take some questions on that portion. Then in the second portion, I'm going to talk about the role of radio networks, V2V networks in autonomous platooning and what the requirements are. About the role that U of M Dearborn is playing in this area. What our contribution is, what our tests have revealed, and what some of the areas of failure are, which becomes a starting for the third. And again, at the end of the second part, I have some questions. And in the third part, I'm going to talk specifically about the CCAT project, what the objectives are, and what the work plan is for the CCAT project. Okay, so, in a glance, what U of M Dearborn is, we are one of 3 campuses of the University of Michigan. We are about 40 miles directly due east of Ann Arbor. 10,000 students, roughly, give or take. About a third of it is in the College of Engineering, and College of Engineering is one of 4 colleges, the other 3 being Art, Science, and Letters, College of Business, and Education and Human Services, Health and Human Services. And within the Engineering and Computer Science, about a little more than a fourth of the enrollment. We are one of 4 departments. computer and information science, mechanical engineering, and industrial and manufacturing systems. And we award undergraduate, masters, and more recently, we've also started to offer PhD degrees throughout the campus, but especially in engineering. You can see that from off the slide. Our PhD is in CE, and we have about 30 students enrolled in it. We are a fairly diverse campus. Vast majority of our students are full-time. Overwhelming majority are Michigan residents. Them go to school being employed, which is a sort of a DNA, if you will. Roughly 1 out of 2 students are first time in their families to ever go to college. The campus was established in 1959 as a donation from Ford Motor Company to the University of Michigan. From the beginning, it was meant to cater to commuters. All 3 campuses share the same set of regions and president. In the case of Dearborn, one of our attraction to the local economy is that 90% of our students, especially in the automotive industry, the electrical and computer engineering department, we do a fair amount of work in electrification and autonomy. And this matrix here talks some of the research areas my colleagues are involved in. And if any of you that are listening in on this webinar want to be connected with any of them, I'm happy to make a connection. We pride ourselves in doing a lot of applied research. So our projects always have a mix of funding from both industry and government. And this CCAT project is indicative of that type of mixing. Of course, the funds for CCAT flow from U.S. Department of Transportation. We also leverage additional funding from the U.S. Army and from the United States Department of Energy. And we have received some funding from OEMs and suppliers on this effort as well. And as I said before, in this project, it involves myself and Paul Richardson as co-PIs. I'm going to start this discussion on fuel-efficient tuning by showing a video. This is a video that was recorded late fall of 2018. And I will pause this to make points, and then I will run this completely. Pausing it for a second to show you that the truck that just passed, truck manually driven. You will see 3 other trucks follow it. There are the 3 trucks, and those 3 autonomously driven. So by autonomous, I mean throttle, brake, and steering are autonomous. And all try to draft off each other by maintaining a closer than normal following distance. Following distance can be as close as 20 feet, as much as 300 feet, depending on different situations, and we'll get into it. And in this particular case, around 100 feet when they're following each other. View of that platoon convoy from another vehicle. Other vehicle from which this video is shot. Make some maneuvers as it relates to this platoon, and the platoon will react to it, and you will see in a few minutes. So this is a highway exit in American Center for Mobility, and we'll come around. What you saw there was that vehicle from which that video was shot trying to quote unquote between the platoon. So between the lead vehicle and the second vehicle, it does a cut in. And when that happens, the follower vehicle increases the gap distance that this vehicle can safely operate within the platoon. And when this vehicle will leave the platoon, it automatically close the gap distance. You can see that when the other vehicle cut in, it gap distance with it as it would with the normal. Of course, those can be programmed in terms of what they are. As this video progresses, you will see various features in the road environment. You will see curvature, you will see a little bit of vertical grade, you will see some bridges, overpasses, etc. And I will make a reference to them in the future. Every one of those presents a challenge from a radio network standpoint and from the standpoint of achieving this platooning feature. This video was taken from one of the trucks itself, the follower truck. Again, on the left, you see this non-platoon vehicle, and you will see it make some maneuvers. So there's a dash display inside. You just saw the vehicle go through an underpass. This is the emergency stop. Another underpass. Another minute and we're done with this. Okay, so I want to acknowledge all the people that have contributed to this effort. In addition to my colleagues at Dearborn, we work closely with Auburn University. They are responsible for all of the control for the vehicle. As I said before, we've received funding from a variety of different sources, and those are all listed in this slide. Why do platooning? Forget about autonomy and radio networks and all that. The reason for platooning is the fact that if you look at a typical truck and if you look at the airflow behind the truck, you see these eddy currents, if you will, as a result of the airflow behind the truck. Whereas if another truck that follows behind, the flow on this truck is very smooth. And as a result of this vehicle, of this air current being very smooth, you will see two effects. The following truck encounters very little headway velocity that it has to overcome. You can see this in this slide. If you can see the velocity profile of the follower truck, you will see that it's all blue, meaning it's very low velocity that it has to brake. Whereas when the gap distance increases, you will see more and more of green, which means that it has to brake a much higher wind velocity in order for it to progress. So it is this ability to draft off the lead vehicle and not encounter the headway velocity that is the compelling reason to do platooning. And you will notice in many of my slides that I point out the references. This particular reference comes from our collaborators at NRO. And what they have shown is surprisingly two things, or a secondary surprise, which is not only does the following vehicle enjoy a fuel efficiency, but as a result of a high pressure stagnation region, this region also pushes the lead vehicle. So the lead vehicle enjoys some fuel economy as well, in addition to the following vehicle. And the graph sort of shows you on the x-axis what the vehicle separation distance is and what the fuel saving is as a percentage of normal. And let's look at the trailing trucks. The trailing trucks, initially they actually become a little worse, but at around 10 feet, 12 feet, they peak and they taper off. So the more further you go, the worse you get in terms of fuel savings. The middle truck, so this is a 3-truck, the middle one is this truck. In the middle one, you see that from the get-go, you get fuel savings and it tapers off as you go. And the tapering off, you can see that it can go anywhere from 18%, 17% at about 5 feet closing distance to about 5% at 90 feet closing distance. Oh, sorry, not 5 meters closing distance to 90 meters closing distance. And look at the lead vehicle. The lead vehicle, because of this this effect, this high pressure stagnation region pushing effect, it also enjoys some fuel economy savings, or fuel efficiency savings. If you look at the trucking industry as a whole, make sure that I covered everything in that one. Yeah. Roughly about 22% of a typical fleet operator's operating cost is fuel. And if you look at society as a whole, Class 8 trucks are the biggest consumers of fuel. And my point being is, whether it be from the standpoint of a fleet operator or from the standpoint of society, there is lots of payoffs in looking at the fuel efficiency for semi-trucks, for Class 8 semi-trucks. Again, for those of you that are interested in more of this, you can look at the references. The trucking industry also has a second problem. If you leave aside the fuel efficiency issue, they have a labor shortage issue. So, just in terms of some statistics, 70% of the freight in the United States move via trucks. You can look at the billions of tons in weight, the number of trucks that are deployed, or the number of truck drivers that are deployed. It's a huge industry, and roughly 40% of their operating cost is associated with the driver. And for a variety of demographic and economic reasons, they are experiencing for several years now driver shortages. So in the latest year available, 2018, compared to the year before, they were 20% short in terms of number of drivers, or 20% more in terms of shortage of number of drivers. And they expect that in 10 years that this number will double. So it's a even if you leave aside the fuel issue, trying to eliminate power for drivers, if you will, I shouldn't use the word eliminate, driver shortages is a compelling value proposition in that industry. So from a semi-truck platooning problem, the normal gap distance for semi-trucks is about 1 truck length if you're traveling below 40 miles per hour, and 2 trucks if you're faster than that. In order for you to realize the fuel efficiency with platooning, you have to follow at very close gap distances. It can be less than 50% of normal gap distances. There are other road factors in effect. You can have other vehicles cut in and out, resulting in sudden braking, acceleration, deceleration, as the case might be. You have vertical incline, so that has to do with gears, road that causes vehicles to gradually decelerate. So my point is that if you're going to imitate platooning as done by a human, then you have to deal with these types of issues, and that's the premise of the next 1/3 of my talk. So I'm going to take a brief pause, and I'm going to take any questions that you might have before I get to the second phase of my talk.
Yeah, it's Randy Johnson. Some guy called Brian.
Hello?
That's okay. No, he left me 2 voicemails.
Please mute your phone if you're not the presenter.
Okay, so if there are no other questions, I will go to the second part of my talk. This has to do with how radio networks and vehicle-to-vehicle communications play a part in this fuel-efficient platooning. So this, for those of you that are joining late, I'm in the second part of my talk. So this is a sort of hardware level architecture, if you will. Again, this is joint work with Dave Beverly and company at Auburn. The innovation, if you will, in our work is that unlike a typical autonomous application, autonomous vehicle application, where you use perception sensors as your primary means of sensing the world, in this particular level 2 truck platooning that we've been able to achieve, we do it with no perception sensors. So the lead vehicle has a very high accuracy GPS. In addition to it, it also has a V2V radio that allows it to communicate information to other trucks in the platoon. Every vehicle in the platoon has a GPS and a V2V receiver. Every truck also has a short range and long range radar, and the lead truck typically doesn't use it unless it's engaged in a cruise control of some kind. But the follower trucks rely on that for their throttle control. So the throttle control and brake is done with the radar input as being the driving force, and the steering is done with the GPS being the driving force. And the V2V provides a sort of a redundancy to both of them. So that's the role of V2V in all of this. And if you're interested in knowing more about the architecture and how DSRC plays a role in the platooning system, this diagram here describes the lead truck. This diagram here describes the follower. There is a legend in terms of what signals are wireless, what signals are physical signals, what signals are CAN and network signals. Again, you can find more details in this reference in GVSETS 2009. What the University of Michigan Dearborn has done is that we have embedded a software on the DSRC radio. So let me go to my previous radio. This radio here is a Kodai MK5 DSRC radio. And on that radio, we embed a software, both on the transmitter side as well as on the receiver side. And this software acts as an intermediary between the Auburn controller radio channel, if you will, or the physical, radio output. It receives information from the host, the Auburn controller, via a UDP port, Ethernet port. It's a UDP socket, and it strips once it receives it, it strips off the UDP information and puts in it the radio specific information and broadcasts it. And then it does the opposite on the other end. So it then it receives the radio, strips it off the radio header, puts a UDP header, and gives it back to the Auburn controller. And this is our contribution, if you will, to this project, is this reliability in establishing this radio network. The way in which the DSRC radio is used in here imposes some fairly severe real-time constraints. And so this level of control over the radio network is needed for us to realize this application. The host computer tries to pass on to the following trucks some vehicle state messages. These messages are up to 300 bytes in length, and every 1/20th of a second, so at a 20 hertz rate, it wishes to pass on this information to the following truck. The following trucks then use that in their controller. In addition to the vehicle state message, the people in Auburn also have a mechanism for differential GPS, where the trucks broadcast GPS information to each other, and that allows them to do some differential correction and localize these trucks much more accurately than without it. And so GPS correction, what we call it, it's about 1,000 bytes in length, and that's also broadcast the same network at 2 hertz. So this is what makes it unusual in the sense that this is not your standard DSRC packet transmission that consists of basic safety message. It's a slightly different use of the same radio. One portion of the message looks somewhat like the BSM. It's probably already almost identical. Another one is the GPS correction. This 20 hertz rate, I want you to keep it as nominal because it can go up depending on the situation. So it can go, we have seen it go up to 50 hertz in some situations. This is a sort of a more detailed explanation of what I said in the last slide. The Auburn system through an Ethernet switch passes on UDP packets to the Coda radio. On that Coda radio is our application. It strips off the UDP portion of the message and puts in it the radio header and transmit it, and then vice versa at the other end. There is also a bridge for RSU, but we are not going to talk about that. The data rates roughly are 8 kilobytes per second transmission rate and 24 kilobytes per second reception rates. These are slightly approximate, so the total is closer to 3 kilobytes. At about 300 bytes per packet, we are talking about a throughput of about 1,100 packets per second in this network. Our software is plug and play in the sense that there is no need to utilize the operational network if the goes down. If the radio is turned off, it relaunches automatically on restart. It can be easily upgraded to a newer version through the SD card. And most importantly, the application allows for a full log of the entire network throughput. This is stored as a CCAT file. Advantage is that there's a number of open source applications like Wireshark that you can use to parse that information. It also allows you to measure the performance index, the key performance indices for this network. I'll give you one example. We can measure the RSSI of the network. So this is the ACM test, and you can see that when you have two vehicles that are about 100 feet apart, traveling at about 50 miles per hour, this is what the plot of the RSSI looks like. In fact, later on I will this formed the basis of our proposal to CCAT, is because we found that this radio network had some failure points or failure modes that that pertain to specific road geometries and environments that we wanted to look at more closely, and that's why we're doing the CCAT project to begin with. You can see that the radio network performs quite well in terms of the RSSI. This histogram is over multiple days. The tests were carried on with different lengths between the trucks. You can see that despite all those variation, the mean of it is minus 70 dBm, which is very good, and with the standard deviation of about 13.6 dBm, which is also very good. Like I said before, the fact we have this embedded application means that we can measure some KPIs very accurately, and this the list of KPIs has grown a little bit. We don't have the new numbers for some of the newer KPIs. We are going to do some more additional measurements in our future data collection. But we have looked at three different types of KPIs. One is RSSI, then packet latency, and network utilization. And you can see that with the normal system, which is a dual antenna system, we expect a network of this type to perform. We're doing quite well. So we're doing well within what the expectations are of a vehicle-to-vehicle network is. And I say expectation is because the controller is still evolving, and so what that expectation is could change in the future. But for now, this is the expectation of how this network will perform. The embedded software also allows us to do some simple tests of dual antenna versus a single antenna. You can see that the RSSI takes a big hit, the latency takes a big hit, network utilization not as much. We also have a real-time radio network status GUI, if you will. So this is a graph that evolves in time. New data gets added to it on the right. So you can monitor this network in real time, if you will, from the cab of any of the trucks. It provides you with the RSSI as well as the latency of these packets. Okay, so that completes the second portion of my talk. If you have any questions, I welcome them before I move on to the third portion.
Can you give us some idea of where the 20 hertz rate came from? And you said it varies. I'm just curious.
The 20 hertz rate came from that a typical, so let me go back a second. So if you look at the controller for throttle and brake, it is an ACC controller. And if you look at the radar, if you will, that radar is operating at a 20 hertz rate. So the controller is optimized for that type of a sampling time. So the radio network, since the radio network is sort of like a, it matches that.
Thank you.
I'll give people another minute or two and then go on to the third part if anybody has any questions. Okay, so we're on to the third part. So give me a second. I just want to make sure that I got. Oh. Let me move this here. So for those of you that are joining late, I'm Sridhar Lakshmanan. I'm on to the third part of my webinar, if you will, on reliable V2V communication for fuel-efficient platooning. The radio network that previously we've tested extensively. We've tested it in ACM. We've tested it in Alabama at the National Center for Asphalt Testing, which is a 2-mile loop. It's an oval loop. This is the test facility. We've tested it on public roads in Southeast Michigan. We also tested it extensively in the province. And through these testing, we identify some failure modes for this radio network. Just we like that it works all the time. Like any sensor, the radio network also has some specific failure mode. And what we show here is the type of failures that could occur from the standpoint of drop back, which is the ultimate failure. I mean, so that's what you are from a control standpoint. But underlying that is a RSSI failure, if you will, or a latency failure that underlies that. And this is an overlay of packets being dropped along that 2-mile path in Auburn. And this is the RSSI image, if you will. And you can see that around the ends and where the packets are failing is also where the RSSI is challenging. I'll talk more about that. And latency is not that, there is not as much variability in latency, but here also you see some extraneous outliers in terms of packets going through the network at more than normal latency. And we have identified that almost all of these types of failures are what one would categorize as non-line of sight failure mode. So it could be as a result of foliage between the transmission and receiving antennas, or other occlusions like tunnels or bridges, road curvatures that causes in a dual antenna system for one antenna to sort of not be functional. Only the inner antenna in the curvature is functional. Where most of these antennas don't have much of a vertical spread in terms of radiation. So if you have a steep grade, that could be an issue. And cut-ins, when you have a cut-in vehicle and the cut-in vehicle causes non-line of sight issues between the receiving and transmission antennas, those failure modes as well. And this is where we started our CCAT project. So a portion of our CCAT project to identify precisely where these failures were occurring, and then try to see if the cellular V2X radio network, the DSRC radio network, would overcome some of these failure modes. So because cellular V2X is so new, we don't have our own modems yet, so we have to rely on other people's data. And one of the data that the 5G people are able to share with us is the Fowlerville data. And the way we're proceeding is that we are developing a computer model that can explain that data. And using that computer model, we want to, quote unquote, design a cellular V2X system. By design, I mean we want network parameters, antenna placements, number of antennas, etc., and then physically test it at various different locations in Southeast Michigan to see how well the V2X performs vis-a-vis the same failure modes. This is one of our most important objectives in this CCAT project. We have a where I'm not the PI, but I'm a co-PI. It's a Ford Alliance project on MIMO antenna design, and some overlap with these tasks that I just described. And in their case, that project, the PI in that project, and I'm a collaborator, is the one that's going to realize a multi-element antenna for a CV2X application. As part of our CCAT project, in order for us to attack this computer model, we have been looking at this software called Winprop and an associated antenna beam pattern software called FICO, trying to behaves and how one effectively. So I'm giving you a sort of a teaser of some of the types of things that we do with it. Here is a transmitting antenna. We're trying to see what its radiation pattern would be when you have a occluding object, prevents it from having non-line of sight with its entire field of view, if you will. And so this is a visual, this is a radiation pattern visual of what happens in a situation like this. It's sort of static. We can also use Winprop to do dynamic. For example, let's say you have in the same one, let's say you have a receiving antenna and the transmitting and receiving antenna moving together. So that's a dynamic scenario. So the distance would go from 120 meters or so down to 0 meters as these two antennas come together. With the antenna, with the Winprop model combined with FICO, we can answer questions as to what the received signal strength would be with antenna diversity versus a single omnidirectional antenna. The answer is it's not the same, obviously, but we want to understand what the hits are. More importantly, where one should place what type of antenna, etc., is one of our objectives. In using Winprop and FICO, we understood some of its limitations. So although this is not part of the original proposal, that we made to CCAT that was funded. We have a sort of a side project, if you will, where we are improving the RF rendering of radiation sources using some computer graphic techniques. And we hope that we can add to the available tools for the community and the V2V when we finish this project. Our immediate next step is simulation of the Fowlerville test track. This is the test track for which cellular V2X data is available. So we are in the process of simulating this Fowlerville data, which involves us getting the exact test environment in terms of material types and sizes and so on and so forth, and precise location of the transmitting antenna. The receiving antenna will go along this test track, if you will, back and forth. And our goal is to correlate the model-based field strength with the actual field strength. We are about 4 months into the CCAT project, and we hope to have more interesting results, which we'll obviously make available to the community at large. And I once again want to acknowledge all the people that made this work possible in terms of sponsorship, as well as in terms of collaboration, technical collaboration, NREL and Auburn, especially our technical collaborators. And that's the end of my webinar, and I'll take more questions. Are ready?
Do you use C-V2X into the vehicle platooning also?
Could you please repeat your question?
Do you use the C-V2X in the vehicle platooning also, the truck platooning, or just?
That's the hope. So right, using DSRC, and DSRC has some known failure modes that are related to non-line of sight. And as we investigate C-V2X and understand it better, and we can optimize it, we want to be able to use it for this specific application. Yes, that's the goal.
Okay. So in the future, you want to utilize C-V2X into the truck.
Yes, indeed.
And you also mentioned the DSRC failure mode. For these failure modes, does any of these involve with it's all non-line of sight, right? It's all some of line of sight.
In some shape or form, it is the fact that your RF propagation does not have a direct line of sight between receiver and transmitter.
If you do have, line of sight, does the DSRC still have failures sometime?
We haven't seen such failures. Almost all our failures are attributable to non-line of sight.
Okay.
Again, we haven't done any antagonistic testing, like let's say RF interference or cyber interference. We haven't done testing like that. So I have to qualify it.
Right. So you haven't really tested any severe weather condition or something like that, right?
I'm glad you mentioned it. So it is. We have some testing coming up in October where we're going to do things like that, where rain and snow are going to be part of our testing.
Okay. All right. Thank you.
Since this is in the DSRC spectrum, have you done anything with adjacent loading? I don't know what channels you said you were using. If you have a higher population of connected vehicles in the arena, have you done anything with how this might affect it?
No, I mean, in our experience, so let me quickly determine what channel 1T9 is, what rings a bell. Give me 1 second. Let me tell you what did our testing in. It's not coming up. Yeah, it's channel 179 unless I can find differently. It's the channel that we use, and
Qualcomm, I know the channel 179 is a 20 megahertz channel. Are you sure you're using a 20 megahertz channel?
give me 1 second. So that's what I want to make sure that I don't speak incorrectly. 178. 178.
Okay, yeah, I don't care whether you're using the DSRC or CV2X. It's the channel utilization of if you're surrounded by a whole group of other participating non-commercial vehicles, what the impact would be.
Right. So scalability is certainly in the future, but the failure modes that we encounter, despite the fact that the channel utilization is very, very small, less than 10%.
This is Jim from Qualcomm with a question, if I may.
Sure.
If you've answered Bob's question to his satisfaction. When you get to the phase of doing field tests with CV2X, please note that the latest valid wheel results that you got from 5G have a 20 megahertz channel at channel 183. Mm-hmm. There'll be a difference in performance if you use a 20 megahertz channel versus a 10 megahertz channel. Mm-hmm. Have you considered that, or do you plan on using CV2X in a 10 megahertz only channel?
We haven't planned that far ahead yet because we don't have any cellular V2X radios that we are immediately planning testing with just yet. But thank you for sensitizing me. I will pass it on to the team and make sure that they are aware.
There are two sets of data. I guess you have a semi-empirical RSSI model, or whatever you did for propagation. You didn't explain that, but we look forward to that. But whatever it is, you got to see whether you use the 20 megahertz latest report or some of the early reports which had 10 megahertz.
Mm-hmm. Noted.
Sridhar, this is Venkat from Danla. You briefly mentioned that there's an RSU also, which you might not have used in test. But how did you plan, or what role would an RSU play in this?
In the application?
Yep.
Primarily as a means to, since you have a DSRC network platoon, we want to be able to leverage the fact that you can use that same network to communicate with roadside units and have information about, basically the TIMs that are broadcast from the RSUs. You wanted to be able to share it within the network. But it's been our experience, at least in testing within Michigan, where these RSUs are physically installed, but it's a little bit of a growing pains for us to communicate with them, because many times they're not turned on.
Okay.
Or if there are some slight issues, at least in the times that we've tested in Southeast Michigan, maybe it'll be different this fall when we test. But to answer your question, our hope was that since you have a radio network, can you piggyback on that network to obtain information from the roadside units that can be shared within the network.
Okay.
Any other questions? Well, thank you all for listening and for participating.
Well, thank you, Sridhar, for that wonderful presentation, and thank you everyone for attending. Hope to see you at next.
Have a good one.